So hi everyone. In the previous lecture, we introduced all the different opamp non-idealities and how to read an opamp datasheet. So I felt that I rushed through slew rate a little bit. I just gave one example of slew rate and moved on. So in this lecture, we will spend a lot more time on slew rate because it's a very important specification. And slew rate is very closely related to the bandwidth of a circuit. Okay, so what is the difference? How do you say by looking at the op-amp output or the output waveform of a amplifier, op-amp based amplifier, can you say is slew rate limiting its performance or is it bandwidth limiting its performance? How do you say that? Okay, whether the op-amp is slew rate limited or is it bandwidth limited? That's the question we need to answer. And we'll take some example problems in this lecture, different set of wide range of problems. And then by solving each one of them, these ideas will become much clearer. Okay. So just to give you an idea how slew rate and bandwidth are related, usually slew rate is a function of, and even bandwidth is a function of the op-amp architecture. We took an example of a very simple 5 transistor, a differential to single-ended converter amplifier like this, and said that how do we measure slew rate? Just apply a large signal input, and then all your current will switch. This, let's call this as IS, as the tail current. All current will switch on one side, that will be mirrored as it is, and this MOSFET will be cut off. So I can remove this MOSFET, and the entire current will flow through this capacitor. And that gives you IS by CL, gives you the slew rate. This is the maximum rate at which the output of this op-amp can change. Okay, and this is a symmetric op-amp, meaning if I apply a negative step, you can show in a similar way that this op-amp will be active, and the rate at which this op-amp can discharge that node is simply equal to minus of IS by CL. That is also determined by the source, the tail current here. Now, if let's say I were to use this as an op-amp, and I'm interested in finding out its gain bandwidth product, how will I find its gain bandwidth product? So first I need to know its DC gain. This is a 5 transistor, a very simple amplifier. You guys must have already analyzed it. Let R out denote the output resistance. Let R out denote the output resistance. In this case, can you say what will be? Let's assume this is device 2 and device 4. What will be R out in terms of R naughts? R naught is your small signal output resistance of a MOSFET, right? It's the drain to source resistance of a MOSFET. What will be that for a differential amplifier? Let's assume the input is differential. What will be this output resistance? Do you guys have any idea? Approximately it's RO by 2 or RO2 parallel RO4. It's RO2 parallel RO4. It's the parallel of these two transistors. Okay. So the gain, I can write it as the gain to be GM times, where GM is the input transistor's transconductance, times R out, multiplied by the pole, the single pole of the system. There is only one capacitor. We'll ignore the capacitors of the other nodes of the circuit. Since only one node is the dominant node, the pole at this node is given by 1 by RC, 1 by R out times CL. So R out and R out gets cancelled, and you are simply left with GM upon CL. Okay, so the gain bandwidth product of this amplifier is simply equal to GM by RL, GM by CL. The slew rate of this amplifier is simply equal to IS upon CL. Okay, the slew rate on the other hand is equal to IS upon CL. Now you know from basic microelectronic circuit theory that the GM of the input pair is proportional to root of the tail current, right? We assume that under nominal conditions, the tail current splits equally. And then from that, we can derive some expressions using some square law equations. You can argue that GM is proportional to square root of IS. So now you see here, I have an expression for gain bandwidth product, which is given by GM by CL. That has some nonlinear dependence. It has some dependence on the tail current source. And slew rate also has a dependence on the tail current source. Therefore, we cannot say that slew rate and the gain bandwidth product are independent of each other. It depends on the op-amp architecture, and in many cases, slew rate and UGB or the gain bandwidth product are related to each other. If your UGB is higher or gain bandwidth product is higher, slew rate can also be higher. Okay, and we will see in today's class, we'll take different examples and we'll see when is bandwidth limiting the system and when does slew rate limit the system. Okay, that's what you need to distinguish between the two. So in the previous lecture, we said slew rate is the maximum rate at which your output can change at the maximum rate at which your output can change. Bandwidth is more of a is a term that we derive from a linear LTA, linear time invariant model of your op-amp, which comes from a small signal analysis that doesn't capture any large signal behavior. Slew rate, on the other hand, is a purely large signal, a large signal parameter. Okay, it's entirely determined by the large signal behavior of the system, of the amplifier. Okay, so we'll start with a simple circuit here. This is a voltage follower circuit. It's given that the input frequency for this circuit is 100 kilohertz, and the gain bandwidth product is 100 megahertz, and slew rate is 0.5 volts per microseconds. I'm interested in knowing what is the maximum value of VP that I can apply at the input so that the op-amp's output is perfectly a linear representation of the input, meaning it should be nearly same as the input. Vi should be very close to equal to V naught. This condition should hold true, right? If your op-amp is in linear mode, linear region of operation, then when I'm using the word linear, I mean linear in the truest sense, when not in the MOSFET's region of operation sense, okay? Here linear means it's in the linear, linear comes from the LTA system linear, okay? That's what I mean by linear here. So op-amp is in the linear mode of operation. So here, if I apply an input signal, can you tell me what is the maximum value of V peak? So since it's a voltage follower, your output voltage also has to. Yeah. So one of you said the maximum value voltage is, yeah, it's not necessarily, yeah, it's close to 5 or 0.5. We'll figure it out. Yeah, you're right. But it's just you're off by a factor. One of you are off by a factor. We'll just figure that out. So if you see, right, since it's a voltage follower, you expect the output also to follow the input. So the same output should appear at the input as same input should appear at the output as well. The slope at the output of this, the maximum slope at the output is simply given by what? Vp times omega in, which is Vp times 2 pi Fin. Okay, that's your maximum slope of your sinusoid. If you were to find, that's the slope at this point, at the zero crossings. This slope should be smaller than the slew rate. Then you can say that the op-amp is not slewing. Okay, that's the condition. So using that condition, I can say your input, your V peak should be less than or equal to slew rate upon 2 pi times Fin. So your slew rate happens to be 0.5 volt per microseconds or 0.5 into 10 power 6 volt per second divided by 2 pi into 10 power 5, right? 100 kilohertz is 10 power 5. So it will be 5 by 2 pi volts. So that's the input that you can apply for 100 kilohertz. If your sinusoid's frequency is 100 kilohertz, then your maximum peak voltage should be lower than 5 by 2 pi, 5 by 6, right? 5 by 6 is close to what? Yeah, 0.8 or close to a volt. So that's your close to a volt is your maximum input signal that you can apply. So keep in mind here, what slew rate tells you is the maximum rate of change at the output. And the maximum rate of change of the output, if you apply a sinusoidal input, it depends upon two parameters. What does it depend upon? The maximum slope at the output, d V naught by dt, assuming V naught is a sinusoid, that depends upon the amplitude of the sinusoid and the frequency of the sinusoid. So if I have to ensure that the slope of the signal, this is the slope of the signal, is less than the slew rate, then I have two parameters to vary. I can either control my amplitude or I can control my frequency. Okay, so that's what I'm discussing in the next problem. In the next problem, it is given that the peak voltage is fixed, that is 10 volts. And why is it fixed? It turns out this voltage follower is driving a load resistance, and you are supposed to deliver a fixed power to the load resistance. And that power, generally, if you take a sinusoid, yeah, and you're supplying a AC power to a load, the power is independent of the frequency of the signal. It only depends upon the peak voltage. It's roughly given by V peak square by 2RL, right? Or you can express it in terms of the RMS voltage, and V peak by root 2 will be VRMS, and that will be VRMS square upon RL. So let's say you are supposed to deliver a fixed power to a load resistance, and it turns out in this system, in the electronic circuit that you are building, you have freedom to vary the frequency. Now, the question that has to be answered here is that I have to deliver the same power, and the sinusoid frequency should be same as the input frequency. What should be the maximum frequency that I can permit? Again, use the same equation. The maximum frequency is determined by the maximum slope of the signal. The maximum slope of the signal is simply V peak times omega n, which is 2 pi times Fin. This should always be lower than the slew rate, right? Slew rate is the maximum rate at which your opamps output can change. So it should always be lower than the slew rate. So if you use this relationship, V peak is 10, assume 2 pi as 6. So 10 times 6 is 60. So your Fin should be less than or equal to 0.5 into 10 power 6 by 60 hertz. Okay. So that will be 5 upon 6 into 10 power 4. Okay, maybe close to 10 kilohertz, right? 5 by 6, maybe 8 or something. It's close to, yeah, so close to, I can say 8 kilohertz, 785 kilohertz, yeah, whatever. 785, 5 by 6, right? Maybe, yeah, you have taken exact value of pi, then maybe you're getting an exact value of 785 kilohertz, yeah. 778, I think. This is what, 10 power 6, right? Yeah, I'll leave the numericals to you. I think it comes to around 7.85 kilohertz or something. Yeah, if you take exact value of pi, that's it. So this problem tells you a very important point, that if you have to ensure that your op-amp is not slew rate limited, meaning if you want your output to be an exact replica of the input, then you have the freedom to control frequency as well. It's not just the amplitude. You can also give, for a given amplitude, you can lower the frequency. Even then, you will be able to get the same. You will be able to design the system within the slew rate limit. Okay, so these are two important things to remember. Now the question here is, the question that you need to answer is this system bandwidth limited? Is this system bandwidth limited? Forget about this 7.8 kilohertz. Let's go back to the old problem. I said the gain bandwidth product is 100 megahertz. If the gain bandwidth product is 100 megahertz, will the system be bandwidth limited? So what do I mean by bandwidth limited? If you have a LTI system, say with some transfer function h of s, and the transfer function of h of s, the magnitude response looks like this. It has some pole. After the pole frequency, the gain starts rolling off. It starts decreasing with increasing frequency. So if your frequency, if your input signal frequency is far away from the bandwidth, then what happens to the amplitude of the signal? Ideally, see, this is the ideal amplitude, which is supposed to be, in this example, it's a unity gain follower. So it's the unity gain. So gain should be 1 or 0 decibels, close to 0 decibels. You want the gain to be 0 decibels, meaning if you apply a sine wave of some amplitude, the output should also be the same amplitude. But if you increase your frequency above the UGB, above the 3 dB bandwidth of this linear system, then obviously the amplitude of the signal is going to decrease. Okay. the amplitude will decrease. So how do you tell the difference between, are you slew rate limited or are you bandwidth limited? We will look at a proper mathematical explanation later. But if I were to ask you a very simple question like this, you are looking at the output of an op-amp, and can you tell by looking at the waveform? No, you're just looking at the waveform. Let's say you're looking just at the waveform. See, let's say it is an LTI system. If I'm passing a sinusoid to an LTI system, what can you expect? Yes. So if you pass a sinusoid through an LTI system, what kind of a shape will be the output? I'm passing a sinusoid through an LTI system, whatever be its bandwidth. I don't care about the bandwidth. What waveform shape? What is the shape of the waveform at the output? LTI system, exactly. It's same shape, right? The shape of the waveform will look exactly the same. It's a sinusoid. For a linear time invariant system, the shape of the waveform will look exactly the same. The difference will come in magnitude and phase. If you apply a sinusoid of frequency, say A sine omega naught t, the output will have some other amplitude, say A dash sine omega. The frequency will remain exactly the same with some phase shift. Okay, you will have some phase shift. That's the only difference. So you'll have, maybe the signal will be shifted in phase and amplitude attenuated. So the most important thing is that if it's an LTI system, the shape of the waveform will look exactly the same, especially for sinusoids. If I'm feeding a sinusoid, it should look exactly the same. But what about a slew rate limited system? If I feed a sinusoid to a slew rate limited system, what do you expect? If I feed a sinusoid to a slew rate limited system, the shape will no longer be the same. Where will the difference come in the shape? Let's assume your slew rate is very close to the sinusoid's maximum rate of change, but slew rate is slightly lower. Where will the shape be different? Will the shape be different near the peaks or the zero crossings? Zero crossings, right? The shape will be different near the zero crossings. Near the peaks, I'm assuming that the slope of the signal is very close to the slew rate, so it will look like this. So that's the way you tell the difference. Okay. So for a slew rate limited system, your waveform will be distorted. If you feed a sinusoid, and if you measure the Fourier transform at the output of the system, which is slew rate limited, you will see frequencies which are not present in the input. You will see harmonics of the input frequency. Okay, that's called distortion. So that's how you tell the difference between the two. So now let's come back to this question. The frequency is 100 kilohertz. If the frequency is 100 kilohertz, and let's say you applied an input signal Vp, which is less than 1 volt, or let's say this, I think this number is, since one of you already did the calculation, it turns out to be what, 0.785. Let's say you applied a peak voltage of 0.7 volts. Okay, will it be bandwidth limited at all? Can I say, is it bandwidth limited or not? So look at this. An op-amp with a unity gain follower mode can be modeled as, yes. So we'll have to look at that, right? See, your gain into bandwidth product is 100 megahertz. The gain into bandwidth product is 100 megahertz. And the maximum input frequency is 100 kilohertz. Since your frequency is 100 kilohertz and the gain bandwidth product is 100 megahertz, you can, if you plot its closed loop response, if let's say I model this amplifier in a linear model, let's say I use a linear model for this op-amp, how will the transfer function look like? The transfer function will look like something this: 1 by 1 plus S upon omega p times A. That's how it look like approximately, right? It is, see what will happen when you put a system in closed loop feedback, your DC gain becomes A by 1 plus A beta. And your bandwidth will increase by omega p into 1 plus A beta. Since it's a unity follower mode, beta is 1. And since A is much greater than 1, the DC gain is close to 1. And the pole frequency is close to omega p times A. So that's what I've written here. And omega p times A is nothing but your unity gain frequency or gain bandwidth product. So I can simply replace this by omega u. Now, this is a first order LTI system with a transfer function that will look something like this. And the pole of the system will occur at 100 megahertz. And you are applying a sinusoid which is at 100 kilohertz, which is well within the bandwidth of the system. So it won't be bandwidth limited. Okay, your frequency is much lower than the closed loop bandwidth of the system. Therefore, you don't have to worry about this. Okay, we'll say that this is not bandwidth limited. So I can argue in the second problem also, because your slew rate itself is so low that the system is limited by the slew rate. Okay, so I'll leave the second one. We'll analyze the third problem. I've taken a different shape for the waveform here. Okay, I've taken a different shape for the waveform. Here we are assuming a ramp signal. Again, the bandwidth is close to gain bandwidth product, GBW. Let's take it's close to 1 gigahertz. Okay, 1 gigahertz is the gain bandwidth product. And slew rate is given to be 0.5 volts per microseconds. Now, can you similarly find out what is the maximum peak voltage that this system, that you can apply to this system? Assume that assume that the supply voltage, the saturation voltages are plus minus 15 volts, meaning your output can swing between plus and minus 15. Take this assumption and try to figure out what will be this. So ideally, if this op amp is just an inverting amplifier, you would expect to see it's just a 180 degrees phase shifted version. So you should expect to see something like this. And the peaks will be 100 times V peak and minus 100 times V peak. And the time period should remain the same, which is 1 millisecond. So can you tell me what is the slope of the signal at this point in this region? What is the slope? It's a very simple linear ramp, right? The maximum slope will simply be 200 Vp, this voltage minus this voltage divided by the time interval. So 2 Vp divided by 200 Vp divided by, what is the time interval? This is half a cycle. So half a cycle is 0.5 milliseconds. One cycle is this. So it will be 400 into Vp into 10 power 3. This is the maximum slope. And you want this slope, 400 times V peak times 10 power 3, to be less than or equal to slew rate, which is 0.5 into 10 power 6. Okay. So from this, you can compute what is your value, right? So 4 into 10 power 5 and 10, you're left with 5 upon 4, which is 1.2 volts. So the input peak that you can apply is 1.2. But is this correct? Is this number right? So if I apply 1.2, will it work? No, right? Because your op amp is saturating at plus minus 15. So you should start with an assumption that your output can go to a maximum of plus minus 15 only. Okay, you did a normal calculation and said, okay, it's 1.2 volts. If you assume your input to be 1.2 volts, that's getting amplified by a factor of 100 times. So which means the output voltage will be 1200. 120 volts. Again, that's not feasible. So output is going to be saturated by plus minus 15. So you have to start with an assumption. Assume that your V swing, I'm saying that your V output swing of this op amp is plus minus 15 volts. Okay, it will be slightly lower, but we are assuming that it will be plus minus 15. So if you assume it to be plus minus 15, now can you calculate and tell me what should be the maximum input peak? If this input is plus minus 15, what is the maximum slope? So you'll have in 0.5 milliseconds. So if this is plus 15, this is minus 15, 30 volts by 0.5 milliseconds. So that will be 60 into 10 power 3. Okay. This anyways is smaller than 30 volts per 0.5 milliseconds can also be written as. Yeah. So let me answer this question. So one of you posed this question that 1.2 is the theoretical maximum that the op-amps lose. That's true. If I did not give you the supply limit, I said, okay, the op-amp is ideal, but its supply can go to infinity. Then what you said is right. So 1.2 is the theoretical input maximum. So in that case, you're assuming the output can go fill 122 plus 122 minus 120. Okay, so that's the assumption that it boils down to. Okay, did I make any calculation errors? So 2 V peak by 0.5. The output is going to be 100 times multiplied. 200 V peak by 0.5 milliseconds. No, I think it's fine. Yeah. So you got it right. That's the theoretical maximum. If your op amp is not saturating, then you're right. You can say I can apply on 1.2 volts and expect an output. The problem is, right, when the output reaches, see, what will happen if I feed a 1.2 volt input to this op amp? Let's analyze it that way. If you feed a plus minus 1.2 volts op amp to this, your output waveform will start getting clipped. It will look something like it will look something like this. It will look, the shape of the waveforms will not look the same. Okay, once it reaches plus 15, which will happen when 15 by 100, when your input voltage reaches 15 by 100, which is 1.5 millivolts. Okay, 0.15 millivolts. Okay, so 15 by 100. So yeah, 1.5 millivolts. Sorry. So when your input reaches 1.5 millivolts, your output will reach 1.5 milli or 15 millivolts, I think. Okay. Yeah. So that's just a calculation, man. You can just do it. So it is 15 upon 100. So once your input signal reaches 15 by 100, your output will start saturating. So your output waveform will start looking like this. See, ideally, you are expecting it to go till like this. You know, you are expecting it to go all the way till this, but that won't happen. It will start saturating. Is this fine, right? So I don't think there is anything confusing here. It's maybe the numerical are confusing, but am I getting your question right? No, all I'm saying is if you apply theoretical 1.2 volt at the input, ideally you should get. No, slewing has nothing to do with saturation. That is true. But if I feed this waveform, I expect, see, when I began the discussion, I said that you have to keep two things in mind, whether the outputs are going to saturate or not. That is the first thing you have to keep in mind. Because if you say outputs are saturating, then it's no longer, it's a distortion. Your outputs are starting to getting clipped. Your outputs are clipped. Your input waveform is no longer ramp. So that's already a distortion. It's one source of distortion. So you have to ensure that the signal is perfect replica of the input with an amplitude, with a scaled amplitude version. That's it. Yeah. Okay. So now let's come back to this. So now I'm assuming your input can go to a maximum of plus 15 and minus 15. So keeping this in mind, now you can calculate the slew rate, the maximum slope of this input. The maximum slope of this input is 30 upon 0.5 milliseconds, which can be written as, because we'll write these units in terms of volts per microsecond, then you can compare it. It's easier to compare it that way. So it will be 30 into 10 power minus 3 by microsecond. So it will be 16 to 10 power minus 3 volt per microsecond. So this can be written as 0.06 volts per microsecond. That's the maximum slope that's permissible for this amplifier. Okay, and this happens to be less than slew rate. So this happens to be less than slew rate, which means you are not at all, the opamps saturated nonlinearity itself is limiting the system's behavior. Slew rate is not coming into this picture at all. Okay, so that's what I mean. Your slew rate is so good. Yeah, see, usually I want an amplified version of this signal. Output clipping means that it's no longer, I gave an example of a square wave. What if I replace it with a sine wave? If you replace it with a sine wave, then you will talk about distortion and all that. You will get more harmonics and all that. So you don't want a clipped waveform. So you want a linear waveform. See, sometimes we purposefully clip it for some other reasons. Okay. Right now I'm talking about distortion, right? There are two sources of distortion. One is amplifier output saturating because of the swing limitation. The other source of distortion is the rate at which the output changes, which is due to slew rate. And it turns out in this example, your frequency is so low to begin with, which 1 millisecond time period, right? That is not limiting. Slew rate is not at all limiting its behavior. It's the amplifier's nonlinearity which is limiting its behavior. So that's what I just want to demonstrate it here. That's it, nothing more. So if your question, one of you asked a question, yeah. So I think it makes sense, right? So you don't want your output to be clipped if you're looking at distortion. I mean, if you want to deliver a sinusoidal signal to the output, then you don't want clipping. That's it. Okay, now this circuit. It's an integrator. I'm applying a step input to an integrator. What will be the output for a step input? It's a ramp, right? If you apply a step, the output of an integrator is going to be a ramp signal. So which means it's going to be a negative ramp because it's an inverting integrator. So it'll be minus of 1 by RC, integral of Vx dt. So it'll be minus of Vx by RC into t. And the slope of this signal is simply Vx by RC. And RC is given to be 1 microsecond. So Vx by 1 microsecond. Again, we apply the same rule. If you want this to behave like an integrator, an ideal integrator, then this slope, the maximum rate at which this integrator's output can change, I'll take mod of this. I'm taking mod of the slope, should be less than 0.5 volt per microsecond. So we can say your Vx, the maximum step that you can apply on either directions, whether it's a negative step or a positive step, to this integrator cannot exceed 0.5 volts. So we took an example of an amplifier. We took an example of a voltage follower. And we also took an example of a integrator. And we showed that for 3 different cases, how slew rate can limit your performance. Okay. And to ensure that your output is not slewing, you have to either limit for example, in case of an integrator, the only thing that you can limit is your peak voltage. In case of a sinusoid, in a regular amplifier, where you feed sinusoidal inputs, you can change either the amplitude or you can also change the frequency. You can decrease. If you see that your output is slewing, how do you see the output is slewing? You look at the zero crossings and feed a sinusoid and see it's zero crossings. If there is distortion near the zero crossings, if the slopes are not tacking, okay, then you know it's slewing. And how do you fix slewing problem? Just decrease the input peak. just decrease the peak voltage of the signal, slewing should be fixed. The other way, if you have freedom to change the frequency, then decrease the frequency also. Even that will work. If you decrease frequency, you will still be able to see the op-amp slewing problem going away. Okay. Yeah. So I've already discussed this difference between, now we have analyzed slew rate for different example problems. Slew rate versus bandwidth. So how do you distinguish between slew rate and bandwidth? You just look at the zero crossings. Okay, for a sinusoid, you need to look at the zero crossings, because zero crossings is the point of maximum slope for a sinusoid. And at that point, you should see that the op-amp's output is deviating from a sinusoidal shape. Okay, it will be ramp for a longer time. A sinusoid will look like a ramp for a very short time near its origin. Okay, and if your op-amp's output slew rate is good enough, your op-amp's output should perfectly track this. It should look like the sinusoid itself. But if it's slew rate limited, then its slope will be slower. Okay, so this, usually there is a word called crossover distortion. So wherein the shape of the waveforms don't match near the zero crossings of the sinusoids. We will revisit this term crossover distortion when we talk about diode detectors and all that. But I'm just introducing the word here. Crossover distortion can be applied here, even here as well. Okay, especially for sinusoids, where you're feeding to op-amp based circuits. You can just look at the zero crossings and see whether it's slew rate limited or not. Bandwidth limited, if I say the system is bandwidth limited, then the amplitude of the signal will be decreasing than your desired value. Let's say you designed it for a certain amplitude level, but that amplitude level turns out to be much lower. Okay, but the shape of the waveform looks exactly the same. And there may be some phase shift. Because, right, anytime you pass your signal through an LTA system, it undergoes two changes: amplitude changes and phase changes. If your signal is well within the bandwidth of the system, well, much lower, if your input signal frequency is much lower than the bandwidth of the system, then phase change will be almost negligible. The amplitude will be very close to the value that you have desired, typically equal to the DC value. So how can you say if your system is bandwidth limited? You'll just quickly see that the amplitude will be much lower. The shape of the waveform will look the same, but the amplitude will be much lower. And that's the way you say the system is bandwidth limited. Okay, it will take some time to digest this. We'll take few more examples, little bit more complicated. So I just wanted to discuss everything related to slew rate and bandwidth in this lecture. So let me see if we have this. Okay. So this circuit again, we are back to this one. Here, now the gain is just unity. It's a unity gain buffer that you're supposed to feed this. And if I feed this as a input to this circuit, you should expect what? Just a flipped version, a 180 degrees flipped version. So you should look like this. Is this circuit slew rate limited? It's given that V peak is 10 volt. Will this circuit be slew rate limited? Its slew rate is given to be 5 volt per microsecond. Will this circuit be slew rate limited or not? It's a unity gain buffer. Input signal goes from plus VP to minus VP to plus VP, and its VP is given to be 10 volts. So output will also go from plus to minus 10. So plus 10, minus 10. Will it be slew rate limited or not? And the time period is given to be 1 millisecond. So half a clock cycle is 0.5 milliseconds. Yes. No, right? It's not slew rate limited, right? Because your slope is very small. Your input free clock, your time period is just 1 millisecond, which means your frequency is kilohertz, 1 kilohertz, which is a very low frequency. And so that will be 20 upon 0.5 milliseconds. So that's 40 volt per millisecond. Okay. Or you can also write it as 0.04 volt per microseconds. Okay. So 0.04 volt per microseconds. which obviously is much smaller than 5 volts per microsecond. Okay, so the output is not really slew rate limited. But if you feed this waveform and then observe the output signal, do you think will the output signal look exactly, do you think it will look exactly the same? If I feed this to a op-amp circuit, where it turns out the slope of the signal is constant throughout this region. It's a ramp signal, right? If it's a ramp signal, the slope is nearly constant. But do you think, will you expect to see the same waveform? Will you think, do you think you will get the same output waveform? Yes. Why do you think it will be smoother at the tips? So one of you said the output waveform may be smoother at the tips. And why is that? Why do you think the waveform will be smoother at the tips? Yeah, derivative is infinity. Or can you guys use some, yeah, the derivative is infinity. That's right. The slope changes, the derivative is not infinity, but the second derivative is infinity. The derivative changes suddenly. The slope changes suddenly. Okay, if you differentiate this waveform, you will get a square waveform. The slope here changes suddenly. So if I ask you a very simple question, let's say you have a LTA system, any LTA system, can it have, if the system has a pole, if the system has some poles in it, okay, then that system's output can never change instantaneously. If you're, especially if you're applying finite inputs, that outputs can change suddenly only when you apply some impulse. Impulse, there is no practical impulse, right? Impulses are not practical signals. Anytime you have a first order RC circuit, if I apply a sudden step input, what do you expect at the output? No matter how high the bandwidth of the system is, the output will always raise with a first order slope, with a first order response, right? And what is the maximum rate of change of the slope? That usually occurs at the origin. And what is that maximum rate? If let's take a first order RC circuit. And if I ask you, what is the maximum rate of change of slope? What will it be? Or what is the maximum slope of the signal? Or maximum rate of change of the signal? What is that? You're right. So it will be, let's assume this node voltage is 0 to Vx. It will be Vx upon Rc. Okay. That will be the maximum rate at which the output can change. That I can write it as Vx times omega p. Okay. Vx is your step input times omega p. So this is the maximum rate at which your output can change in an LTA system, for a first order LTA system. Okay, for a step input. If I feed a step input, your output cannot change faster than this. Okay. So, which means even though if your input signal is a step, your output is smoothening out. If you look at a signal like this, it's a ramp signal. If you take its Fourier transform, it's a periodic signal. Therefore, its Fourier transform will contain impulses, you know. What is the maximum frequency until which this Fourier transform will be non-zero? I mean, what are the harmonics present in the signal? Can you guys roughly say? It's a ramp signal. What kind of a harmonics will they contain? So always remember this result. It's a very useful trick when to remember. Think like this. If you start with impulses like this. If you have an impulse train, usually the impulse train, the Fourier transform is also an impulse train, which means frequency domain will contain impulses at all harmonics. If you consider a signal like this, so is this an even? This happens to be an odd signal. Okay, which means you can always find out a point around which the waveform in a single cycle will exhibit odd symmetry. Odd symmetry means f of x equals minus of f of minus x. This condition. If a signal obeys that condition, you can say that the Fourier transform will contain only odd harmonics. So it will contain 1, 3, 5, f naught, and so on, where f naught is your input frequency. Okay. So if I have a, if I start with impulses and with one positive, one negative impulse, and the time between these impulses is 1 by f naught, then the Fourier transform will contain only odd harmonics at f naught, 3, f naught, 5, f naught, so on. If I integrate this signal, I will get a pulse signal. I will get a proper pulse signal. Integrating in time domain amounts to multiplying it by 1 by f in frequency domain. So what happens is that your frequency content, first harmonic will be highest, third harmonic will go down by 1 by f. Since the frequency is 1 by 3 for an impulse, it'll be 1/3 of the peak, first harmonic. The fifth harmonic will be 1 by 5, and so on. Amplitude will keep decreasing as you move away from the harmonic values. If I integrate the square wave once more, now what I'll do for the square wave, right? I'll subtract the DC value of the square wave so that the DC value is gone. Okay, so now I have a square wave which can go both positive or negative, plus minus. If I integrate square wave once again, I will get a ramp signal. I will get a ramp like this. Okay, so I'm removing DC. Otherwise, your ramp will just keep increasing. So by removing DC, it will always be a contained, well-contained ramp signal. It'll oscillate between two values. That's it. So you will get a ramp signal. One more integration. So if you integrate it once more, it will be, for your Fourier transform will decay as 1 over f square. So you should expect if the first harmonic has some level, this will be 3 square, 5 square, and so on. So you will have infinite harmonics. All harmonics will be present in the signal. But the powers of the harmonics will keep decaying down. It will keep on decreasing. Okay? So what happens here is that whenever you have sudden changes in the signal, see, essentially, what is Fourier transform, right? It's nothing but you take a sum of sinusoids, add those sinusoids, you should get this sinusoid back. You should get the input signal, periodic signal back. But sinusoids are continuous functions. Okay? And here, if you see, right, this is a discontinuous, and you have a signal which is varying very fast, which means you will need a very high frequency signal to construct that region in the signal. Okay, so you will need a very high frequency sinusoid. But the moment you pass it through an LTI system with a finite pole, that's going to filter out all the high frequency harmonics. It's going to kill all the high frequency harmonics. Okay, even though this bandwidth, I have not given the bandwidth here. Let's assume 10 megahertz is the bandwidth. So 10 megahertz and 1 kilohertz, that's like 10,000 harmonics are already included. Okay, so and then because of I'll talk about this UGB thing little later, but you have to be worried about 5 megahertz because the bandwidth of interest will be A beta times omega p, and A into omega p is given as 10 megahertz, that is your gain bandwidth, into beta. Beta for the circuit is half, R and R, so beta is half, so it will be 5 megahertz. The closed loop bandwidth of the system will be 5 megahertz. So still, right, you are getting how much? 500 harmonics, 5,000 harmonics. 5 megahertz divided by 1 kilohertz. That's 5,000 harmonics. So more or less, most of the harmonics are included. So if you actually build this circuit using op-amp, assuming the UGB of the op-amp is 10 megahertz, you should see almost, the waveform will look almost the same as the input waveform. The difference is your tips will be slightly smoothened out. If your ideal tip is like this, the actual tip will be smoothened out like this. Okay, and that smoothening effect comes because of the finite bandwidth. Okay, it's eliminating all the high frequency. You will need much higher frequencies to get this sharp edges. See, Fourier transform is approximating a signal using sinusoids. To approximate a signal which has a sudden change like this, you need a sinusoid of much higher frequency. But because your low pass filter is filtering out, let's say 2000th harmonic signal or 2000 in some odd number, that's 2000 close to 2000 harmonic, that's getting removed. You will not be able to construct a real perfect waveform at the output. So you will see some smoothing out of this waveform, and that happens because of finite bandwidth. Okay, and an intuition to look at it is, it's like this. If you have an ideal step signal, if you feed it to a first order system like this, your first order system will not have a sudden jump, but it will raise like this. If you keep reducing the capacitance value, it'll go closer and closer, and eventually it will approach a step if your cap value goes to 0. When your cap value goes to 0, your bandwidth becomes infinity. Okay, so it will be a smoothened out version. So that smoothing happens because of finite bandwidth. Okay, let's come back to this circuit. Another circuit. I'm again, see, this is again to illustrate you guys. I'm talking all these things because it's useful to understand when will bandwidth limit your system and when will slew rate limit your system. So look, this is again a very interesting example. I'm feeding a pulse input to the signal, an amplifier. Okay, and I'm looking at the output waveform. If I look at the output waveform, it will be minus 10, right? It will be multiplied by this. Ideally, it should just be multiplied by a factor of minus 10. So you should see a waveform like this, plus 10, minus 10, plus 10, minus 10, and so on. But because if I'm giving you the UGB of the system happens to be some 100 megahertz or so, let's assume the input frequency is few kilohertz, tens of kilohertz. Okay, what will be the approximate closed loop bandwidth of the system? Can you roughly say what will be the closed loop bandwidth? The closed loop bandwidth will be omega p into 1 plus a beta, which is approximately equal to omega p times a beta. Omega p times a is the gain bandwidth product, which is given to you. Omega u times beta. Yes. So omega p approximately 10 megahertz or 10 by 11. I think 100 by 11. So beta is 1 by 11. If you see beta happens to be 1 by 11, so you will get this to be 100 megahertz by 11 megahertz, 100 by 11 megahertz. So which is close to 10 megahertz. Yeah, 9 megahertz or so. So that's the maximum bandwidth of the system. So if I take a linear time invariant system with a given the bandwidth of the system, and if I'm giving a step input to that system, the maximum slope or the maximum rate at which the output can change is what? Vx by Rc. Okay, I'm assuming it's a first order low pass filter. So Vx is the input. So Vx by Rc will be that's the maximum slope with which your output can change. This is the slope that's determined by the bandwidth. Okay, if this happens to be much lower than slew rate, then you are bandwidth limited. So what happens is that ideally you are expecting what? This is, let's assume this is some V peak minus V peak plus V peak multiplied by 10. You are expecting to see a waveform that looks like this. 10 times V peak. So this is minus 10. This is plus 10. And what you are seeing here, it looks somewhat like this. Okay, it looks somewhat like this. If you look at this waveform, it looks somewhat like this. This waveform, you can say it is bandwidth limited. Okay, I'm taking an example to show you because this is a step input. So we don't really worry about distortion here. I'm just feeding a step input which contains all harmonics. Here, distortion is not a concern. Whether your output is able to reach its desired value or not. So this is minus 10 V peak and plus 10 V peak. And this slope is given by, see, the total step change, the step change is 20 V peak. That's the step change. Divided by your UGB times beta. Oh, sorry. Multiplied by UGB times beta. This is your maximum rate of change. If this number happens to be less than your slew rate, then you are bandwidth limited. Okay. But if this number happens to be greater than your slew rate, then you will end up becoming slew rate limited. Okay. Your output has to change. But the maximum rate at which the output, your output cannot, your opamps output instantaneously cannot go from -10 to +10. Right? There is some capacitor at the opamps output which is getting charged by a current source. If it's an LTA charging, linear time invariant charging, then its shape should look like this. It should be a first order shape. If it's a slew rate charging, it should look like a ramp. So it will look like a ramp like this. So now, let's say you don't want to, let's say you don't know the values. You don't know what the slew rate values, what the UGB of the system is. You don't know these. Okay. So I'll just mention this point here. I directly wrote 220 VP times the UGB of the bandwidth of the system. That comes from this. If I feed a step input, the magnitude of the step is Vx to a first order low pass filter. Then the maximum rate of change of the output is Vx by Rc or Vx times omega p. That's the maximum rate at which your output can change. Okay. So that's why I said that for this system, the maximum, because this is the opamps output, and I said opamps output is a first order system with a certain UGB. So then you can treat 20 V peak into omega u times beta. That's your closed loop bandwidth. That's the maximum rate of change. If that is less than or equal to slew rate, then your slew rate is letting you change even faster. But your bandwidth is not allowing you to change higher. Okay, that is limiting you. So then you say it's bandwidth limited. But if this number is greater than slew rate, okay, which means your output is supposed to change faster near the zero crossing or near this step change point. But since your slew rate is lower, that change will not happen. It will change slower. It will change little slower like this. So let me draw it again. So this is the change you are expecting. You are expecting this change, but your slew rate will let it increase this way because the slopes will not match. Okay, so that's why you see whether it's bandwidth limited or slew rate limited. But if you are given an exercise where you, by just looking at the output, you should be able to say that. Or I'm giving you freedom to perform some experiments and conclude whether you are bandwidth limited or slew rate limited. What experiment can you think of? Look at this slope. If you are bandwidth limited, yes, the closed loop UGB of this, the closed loop bandwidth of the system is simply given by omega p into a beta, which is simply equal to omega p into a beta, which is simply equal to the gain bandwidth product times beta. This is your omega closed loop. And that I'm calling it as the closed loop bandwidth. So when I'm saying here, 20 volt V peak, 20 times V peak multiplied by omega CL, I'm calling this as your bandwidth. So look at this expression. The maximum slope due to the bandwidth limitation is still proportional to your step input. So what can I do is that if you want to verify your bandwidth limited or not, just double your step or slightly increase your step by some factor alpha. The slope at the output should also increase by the same amount if you are bandwidth limited. If you are slew rate limited, this slope will not change. Even if you change your input peak levels, this slope should not change. Then you know your slew rate limited. That's it. That's one brute force way of just finding out by just varying the input levels on an experiment. Okay. So that's it, guys. We have covered some discussions. I'll open up for doubts because I think that it can have some confusions here. So I'll record this doubts part as well. So if you guys have any doubts, you can ask me now on bandwidth versus slew rate. Okay. So no doubts, that's good. So, so tell me this, the questions that I'm going to ask. If your output system is slew rate limited, can you say it is suffering from distortion or not? If your output is slew rate limited, yes, right? So it is bandwidth limited. So one of the questions I'm getting here is that, so in essence, all steps and sawtooths are bandwidth limited. Yeah, see, usually when you feed a step input, right? Let's say if you guys are feeding 1 kilohertz input to your op-amp, the waveform will look like a proper step input. Okay, or it will look like a proper periodic pulse input when you see it on an oscilloscope. But if you zoom in this region, right, and look at it in these regions, then it will have this first order charging response. It will look like a first order charged response. Okay, so this is a fundamental property of LTA systems. I'm not sure if we can use the word bandwidth limited. When can I use the word bandwidth limited? Is when something like this happens. When your output is not able to fully charge within that time, it goes like this. Okay, your output waveform amplitude itself is decreased. Okay, then for a pulse signal, we can say we are bandwidth limited, right? Here you are seeing amplitude itself is decreasing. The amplitude of the waveform itself is decreasing. So here clearly we can say it is bandwidth limited. So in fact, you will see such waveforms in your wireline communication systems. Okay, and there is a big field of again, this is, since you guys are just in your third year, we will do we do something called equalization to deal with this problem and all that. But when do you say bandwidth limited? If your output is able to go back, if you're feeding a clock input and your output is able to reach to a peak value within that time interval, then you are fine, right? You're no longer, since you're feeding a pulse, for all practical purposes, this will look like a pulse signal to me, okay, for any external circuitry. So that's not a big problem. But when will bandwidth be an issue is when it takes much longer. Your time constant of this other bandwidth is much lower than the frequency of the signal. Then in that case, it won't get time to fully charge to fully charged to the peak value. It'll do this. Okay, so when you see a waveform like this, clearly you can say this is bandwidth limited. Okay, even slew rate did not do this. Bandwidth itself can do this. If your frequency is sufficiently high, bandwidth itself can do this. For sinusoid, it's a very clear cut. You can see that the amplitude of the sinusoid goes down. So we say, okay, its bandwidth is limited, therefore it's attenuating the amplitude. Okay, I'll stop at this.